Okay, let's end this night with some fun dynamics. This problem won't be too bad because it's just a fundamental problem, so it's more about the understanding and the ideas rather than some complicated math. Okay, to start this problem, we should read it and ask what and see what it wants from us. So it wants the acceleration of the cabinet and the normal reaction at these points. So I could start by drawing a free body diagram. And if I draw this free body diagram, notice that this shape is not just a point, it's like a cabinet. It's like a legit cabinet. So we're saying that it has some center of gravity at G. So that's important to realize when we later on talk about moments. But since it's on a surface, it does have a normal force pushing it straight up, perpendicular to the surface, right? But then it does have weight that's coming straight down on it. Exactly straight down. And then since this weight, this is all the forces there is, there's no friction here. But then if we want to draw a better free body diagram, what we can do is we can write it like this. So we put the normal force up here, and we see that the weight will have the weight in the tangential direction, and then it will have weight in the normal direction. Right? And that's all because weight comes straight down. This is just big weight. So this is really what we will be really using here. Okay, and then you could see that obviously this thing has motion, right? So it has motion coming down in this direction, right? It's not floating up, but it's coming down. So this should make sense. This diagram will tell us a lot of information and tell us how we're going to set the problem. Okay, since I want to know the acceleration coming down, it's not accelerating up or down. It's only accelerating coming in the tangential direction. Let me say that again. It's only accelerating in the tangential direction. It's not going up or down, right? This cabinet's not going to float up or go into the earth. It's just coming down the slope. Okay, so we say the sum of the forces. Let me write it better. The sum of the forces in the tangential direction is equal to MAT, right? And then we see that MAT is simply just going to be equal to the weight T. Okay, and for the purpose of this, I will draw this as MAT positive. And then for our normal forces, I'm going to draw it like this, and this would be MAN positive. So this is my new axis system. Okay, so we see that weight is going to be weight in the tangential direction positive. Okay, but what is weight? So weight has two components, weight in the tangential direction and weight in the normal direction. Well, okay, so what it really means is that there's going to be a trigonometric function applied with this angle. So the weight in the tangential direction, there's a lot of weight pushing down in the normal direction, right? So it's going to be cosine of 15 for the normal direction, and that's going to be sine of 15 for the tangential direction. So it's going to be mg sine 15, and then mg cosine 15. And the reason why I know it's cosine and sine in this order like this is because, like I said, right, it's a small angle, so again, if most of the weight should be pushed down in the normal direction. Okay. And I'm just going to write this as W sine 15, where W stands for the norm of the weight, right? So just the magnitude. And cosine 15. Let me make that cosine look a little bit better. Cosine. Okay, so then I want AT. AT is going to equal to WT divided by M. WT is going to be what? It's the same thing as mg sine 15 divided by m. See the masses cancel? So then we're left with just gravity sine 15. And then I'll put this in the calculator. So we know gravity to be 9.81, but we don't know what sine 15 is. And we also need to put them in the calculator to times it. Okay, so we get 2.539 meters a second squared. And we should indicate that that's going in this direction, right? Okay, so that's our answer. Like, we're almost done. We just need the normal forces. So for the normal forces, we can see that if we do the sum of the forces in the, not y direction, but in the normal direction, we have MAN. And like I said, since this thing is not floating, right, it's not going anywhere in the normal direction, it's staying still. So it's at equilibrium with respect to the normal direction. Okay, now, since it's at equilibrium, that doesn't mean it's just equal to 0 completely. I mean, it is equal to 0 completely, but 0 is equal to what? It's going to be equal to the weight in the normal direction minus these reactions. So NB and NA, and then minus WN. Okay, so then we see that WN is equal to NB plus NA. And WN is equal to what? It's equal to the mass times the gravity cosine 15. Okay. Now, you don't know what NB and NA is, and your goal is to find them. So, you're lucky that we have one more equation we can use. We got the sum of the force in tangential, normal direction. But what if we have a length? Right? If we have a length, then we can have a moment equation. So, we have the sum of the moments about point G. So, coming down onto this point here, we're going to take all the moments. So, if I draw the diagram again, and I'm going to draw it kind of like a rod. Actually, no, I'm not going to draw it like that. I'm going to draw it just like how it is, so like an actual shape that it is. So this is G. Then we notice that here's A and here's B. They're pushing up, right? Okay. And then that we're going to note that so this at point G, it's accelerating in this way, right? So this is MAT, right? Okay. And then the weight, we know that it's coming straight down, right? So basically, these two forces, we don't need to even worry about them in our moment equation, because if you think about it, right? So if we write out the moment equation, and like I said, this thing is not rotating, right? It's just standing still, but going down the hill. So it's going to be 0 is equal to MAT plus the distance from G, since we're taking the moments at G. So what's the distance? What's the radial distance from G? It's 0. And then what's the radial distance for the weight? It's 0. So we don't even need to think about those. We can just cross them out here. However, the normal reactions here, both NA and NB, do have some distance between them, between G. Right? So it has this distance right here, the radial distance between G. Okay. And notice I'm not going like this. So when you take moments, the radial distance is the distance opposite to the direction of the vector. Or you could say the radial distance is perpendicular to the direction of the vector. Okay, so if you had like your arm, and if you push your hand down on your arm, and you're taking the moments at your elbow, the radial distance is my forearm, right? Okay. So we have NA and NB. Now we don't know if NA and NB are positive yet. We don't assign signs to them, really. But what's the distance between them and G? It's 0.5. So 0.5 and 0.5. Okay, now it's time to start thinking about the sign. So pretend my arm is the cabinet. And then here's at point B. Actually, my bad. I drew the diagram slightly wrong. The first wheel is B. The second wheel is A. Okay, so to pretend my fist is the wheel A. So if I push if there's the normal force NA pushing it this way, my arm is rotating in what direction? It's rotating in the counterclockwise. So NA is positive. Now, if we're to push my finger at my elbow, my arm is now rotating in the clockwise direction, and we consider clockwise negative. So we get this, and this is all we really need here. And we can see that NA is equal to NB, right? If we factor out the 0.5, and then since it's equal to 0, we can put this on this side. So NA is equal to NB. So now we can sub it back into this equation here. Okay, so if we go NA is equal to NB, then we could write NB to NB is equal to mg cosine 15. And then we could find what NB is. NB is going to be equal to mg divided by 2 cosine 15. And I'll put this in my calculator for you guys. By the way, remember the mass is 80 here. So I can write it as m is 80 and divided by 2, so 40 gravity cosine 15. I'll put this in the calculator. Okay, so we get about 379 newtons, right, if we put that in the calculator. And then we know that NB is equal to NA, and both of them are equal to 379 newtons. And then we should label the direction that they're pointing, because they're vectors, and they're pushing up, right? So there you go. There's your answer. That's your second answer. The problem only asks us for 2 things, and that's it. There we go, we're done.